Good evening, students. Okay, now let me start with one more video on getting the frictional coefficient for a mass which is being dropped from here. It hits the spring and again rebounds. So there's a uniform spring, there's a uniform frictional coefficient here. So we need to determine what is the frictional coefficient. This is the problem. Most of the time, students face a problem in solving these kinds of numericals. Okay, what is the reason? The reason is simple, that whenever we discuss about springs, we discuss about two things, two types of equations. One is forces, other one is energy. Okay, sometimes we use force, sometimes we use energy. Now, when to use force, when to use energy is a biggest question. Okay, this is something which many students make a mistake. Okay, so Abhi, so let us start with this particular problem. A small block of mass 2 kg. This is a problem from HCV. Okay, so this is a mass of 2 kg. Which slips down the incline to a point from a point 4.8 meters away from the spring, which means from here to here, the distance is 4.8 meters. 4.8 meters. The block compresses the spring by 20 centimeters, which means this spring gets compressed and this becomes like this. The block is now in contact here at this point, which means the distance here is 20 centimeters or 0.2 meters. Okay, stops momentarily. So it hits it and it stops, and then rebounds to a distance of 1 meters. Okay, then what happens? It goes upwards by distance of 1 meter. Then once again, it springs back like this. Springs back like this. Okay, this comes to equilibrium point, but anyway, it goes beyond a little bit here. So this mass keeps on going until here. So therefore, the distance once again from here to here is seen to be 1 meter. As I have drawn all the three scenarios. The first scenario, where does the block start from? Second scenario, let me call this as first scenario. Second scenario, the block comes and hits the spring and it compresses the spring. The third scenario, after rebound, okay, the block is at this point. Okay. Find the frictional coefficient between the plane and the block. So I had given the students when I was teaching for Fiji, and at that moment, most of the students, I got an answer like this. And the reason they gave me is, he said that the restoring force on the spring is given by Hooke's law, which is F equal to minus kx. Okay. Now towards it, what is the force acting at this point? When the block just touches this, okay, let me write this once again. When the block touches just the spring over here, this is my normal force. Let frictional coefficient be mu. This is my angle theta. So therefore, this is my mg, and this is my line which is parallel or anti-parallel to the normal line. Okay, and then I'm going to resolve this mg along two directions. One is along the normal, so they should be theta once again. You know how to get this theta, right? If this is theta, this is 90. This angle should be 90 minus theta, and this should be theta once again. Okay, so therefore, this is my mg. This should be mg cos theta. So downward mg cos theta, and here it is mg sin theta. I will resolve this mg force into 2 parts. Okay, after doing this, now let me write the force equations. So therefore, normal force is equal to mg cos theta. Normal force equal to mg cos theta. It's balanced by it. And then the frictional force here is given by mu times A. Mu times A. Now the block is coming downwards. So therefore, what I should do is I should write the net force acting on the block is nothing but mg sin theta minus mu times n. This is my net force. Why mu times n? Frictional force. This should be equal to ma. Okay. Now this is the force that is acting at this point. Now because this force is acting, this compresses the spring downwards. I hope this is clear. It's clear. The force equation is correct. Okay, nothing wrong. Okay, this is correct. Then now let us start with this part. Just a moment. Hello. Okay, fine. I'm back. So we have, I have written the equation for the force equation for the downward motion. Now the moment the spring hits it, now what does it do? It compresses it. Okay, and once again, the spring is now throwing it outwards. Then when it is going outwards, let me draw the inclined plane once again. This is my inclined plane theta. Now the object is here. Okay, earlier it was here, now it is here. Now while it is going upwards, now what is the force acting? Now once again, if I do the same thing, mg sine theta, it doesn't change, right? Because normal force is like that. It's always been pulled by gravity downwards. So mg sine theta is like this. Nothing wrong. And this friction, when the object is going like this, friction should act like this, right? So as a result of this, this would be mu times mg cos theta. The difference between this and this diagram is that, see here, mu times n was acting upwards. Why upwards? Because the object is coming downwards, right? So friction always opposes relative motion. Now here what happens? The object is going upwards, so it should be acting downwards. Okay, not this direction. It is this direction. Okay, don't get confused. Okay, so therefore this should be downwards. Thus the restoring force once again should now be equal to mg sine theta plus mu times mg cos theta should be your restoring force. Okay, now if that is the case, this equation also correct. Now it's the same restoring force. Why is the same restoring force? The reason is because you have a spring. Let me take up, okay, let me do it here. So I have a spring, I give an object, okay, I place an object out of it. The spring is now like this. Now when I place an object over here, it gets compressed like this, right? It's like this, now it gets compressed like this. And then, okay, when the object is supposed to be removed, then this spring expands like this and throws it upwards. Which means the force what I have received, the same force should be given back also. That is what is the misconception. Okay, did you realize it? So what is the misconception? You have assumed that the force that I am giving back, okay, it's the same force that I have received it over here. Okay, let us see that. So as a result of it, what the students generally do is they equate these two and finally get an answer for mu. Solving this, you get a value for mu equal to 3/4, which is incorrect. Okay. So in such cases where there is a friction involved, do not use this force method. Okay, this is very, very important. This is equally applicable only when you can apply it. When can you apply? When you can apply it when there is no friction. Though the restoring forces in both of them could be same, but some amount of energy is lost in the friction. That has not been accounted for here. Okay, so as a result of it, you should not use this. But now, let me show you the correct way of doing it. So I hope you realize the misconception. Whenever an object is under a constraint force, okay, what is a constraint force? Or maybe in a non-conservative force. What is it? Which means that when you have a non-conservative force, then there's some amount of energy being lost in some process. It could be due to friction, it could be air resistance, drag, it could be viscous force, whatever it is. Okay, some amount of energy being lost. In that cases, do not employ your force equations. Very, very important. Use energy equations because you can account for what is the energy loss. Okay, now let us work on that. Now towards it. I have already worked it out here. Okay, so here, so the answer, just a moment, there's something wrong. Let me rectify this so that I don't give you incorrect values. Okay, the mistake was the value of mu is 0.5. I had already worked it out. Okay, nothing great. The moment I see it, I'm not getting the answer. Okay, before I do it recording, I just work it out once again and see, okay, where could be the mistake? How do you resolve it correctly? Right. Now towards it. Now once again, use the same formula. What are the formulas that we had? We had a formula which is the downward motion. Okay, let me do it once again. In the downward motion. So now I'm going to apply your conservation of energy. Conservation of energy principles. When you apply the conservation of energy principle, now what is the energy here at this point? The energy at this point, or maybe I will use one thing. I'll just do the work done here because either you can use it mgh and half mv square. But when I use that, I do not know what is the velocity at this point. Okay, so let me use your work done. Okay, so therefore, the total force acting on this object is nothing but when it reaches here, when it touches this object over here, is nothing but mg. Let me write down here. This is mg sine 37 minus mu times n. The same equation I have written. The same equation I have written. Why did I use the same equation? The reason is because this is a force. Say this force is the same here or it is here. Okay. Now what is this distance? This distance is 4.8 meters. Does it experience a friction here? Obviously it experiences. Now the moment it compresses it, does the force change? The force does not change, right? So it compresses until a distance of 0.2 meters. See, this force is dependent on m and g. When it compresses also same mg. Sine 37 is not changing. Mu is not changing. N is not changing. So therefore, the total distance traveled in its downfall is seen to be 4.8 plus 0.2, which is equal to 5 meters, right? There's one more mistake many students do it. Okay, they just consider only until here. They don't consider this one. Okay, so it's totally 5 meters over here. So that's what has been done. Mg, I've taken common here. This n, the value of n, as we already have seen, is nothing but mg cos 37. So I've taken this outside. So I get mg into sine 37 minus mu cos 37 into 4.8 plus 0.2, which is 5 meters. This should be equal to, this is a total work done by the object. When I said I'm doing a work, now how did I do a work? I had a lot of potential energy here. This potential energy is being spent by me to keep on coming downwards. Now, as I keep on coming downwards, my potential energy is reducing. Okay, when I reach here, potential energy is still higher. Then this energy is now given to the spring. As a result of this, I'm losing all my potential energy, giving it back to the spring, right? I'm giving it back to the spring. Now the spring gets compressed as a result of it, right? So when you give energy, only spring can compress. So as a result of it, this is a compression means. The total energy given by the object in moving by a distance of 5 meters is being given as a spring energy, by which the spring gets compressed by x. And the value of x is seen to be 0.2. Okay, we get this value here. Now, after getting this energy, what should the spring do? Spring says, I'm not happy. Okay, I don't want to get compressed. I'm going to throw you out, right? So therefore, this energy is once again released, right? So once it releases, now what happens to the object? The object springs backwards. It moves backwards, right? So this should now be equal to mg. Why? So once again, you see mg into mu cos 37, or mg, or I can say that this is nothing but your mu times n plus mg sine 37. You know how did I get this, right? So I had drawn already the object, and this is your mg sine 37, and this will be my normal force. This was my mg, and this was 37 degrees, and this was my mg cos 37. And as a result of it, I just substituted n equal to mg cos 37, and your frictional force now is in the downward direction. Why downward? Because the object is moving upwards, right? So I have added these two. Now, see, in the previous example, what did we do? We just equated the forces. Now we are not equating the force. Okay. So the energy gained by the spring is equal to so much. The energy released by the spring, not lost, energy released by the spring is equal to mg into mu cos 37 plus sine 37 into 1. What is this 1 here? It's already given here. It's moved by a distance of 1 meter. 1 meter. So what? And similarly, we should write something here, right? This distance. What is this now totally? This is F, this is S, right? Work done. Then here also you see, this is F and this is S, right? You can always say, where is this Fs cos theta? The theta here is F is like this, S is also like this, cos 0, right? The angle between them is 0. You should not take 37 here, okay? So 37 is used only to compute the normal force, right? Okay, so therefore, now you see F dot S will be F into S. Similarly, while it goes backwards, what is the force acting here? Force is acting in the upward direction. S is also in the same direction. And this we have got this one. Okay. So now let us equate these two. Okay. I need not find out this value. So I get this as mg into sine 37 minus mu cos 37 is equal to what do I have here? Mg into mu cos 37 plus sine 37. Guys, I hope you are getting this. Okay, so what I have done is I equated this equation with this equation. Why did I equate? Because the energy gained by the spring is equal to energy released by the spring. Spring cannot release more energy, less energy, right? Whatever it gains, it has to release. Okay, I just equated this. So cancel these mg's. And hey, I missed something here. Okay, this is into 5. Into 5 here and into 1 here. Into 1 here. Okay. So therefore, now I have 5 sine 37 minus 5 mu cos 37 is equal to mu cos 37 plus sine 37. Now you see this sine 37, this is sine 37 here. So this should become 5 sine 37 should now be equal to 5 mu cos 37 plus mu cos 37 should be 6 mu cos 37. Now this implies now I can write this as 4 sine 37 divided by 6 cos 37 is equal to mu. Okay, I have eliminated all the factors, pushed it on the other side, I got the value for mu. Now this should be 2 times, this is 3 times. 6 got cancelled 3 times. And thus I get this as 2 by 3 sine 37 by cos 37 is tan 37. Tan 37. Now what is tan 37? I hope you know this rule. This is your angle 37 degrees. This is your 4, this is your 3, this is your 5. Okay. So tan 37 is nothing but 3 by 4. This is to be 2 by 3 into 3 by 4. So 3 and 3 goes away. I had a 4 here. 4 here. 2 ones are, 2 twos are. Thus the answer should now be equal to 0.5. Okay. Which is the answer. Problem seems to be very simple, but look at the intricate details over here. HCB problems are really wonderful. Okay, when you start solving one by one all these problems, you will really get an edge on the topics of physics. Thank you, friends. So whenever I find such interesting problems, okay, I'll just post it across. And in fact, this problem was posted to me by one of the viewer. He asked me, she asked me whether can you solve this problem because I was not able to understand this. And she had done it like this. And even the school also, they did it by the same method, but they didn't get the answer. And they thought that HCV solution was incorrect. HCV solutions, most of the time, I have not seen incorrect. Hardly, I have never seen any solutions to be incorrect. Most of the time, it's correct. Okay, so somewhere our understanding about the numerical might be wrong. So this is what initially I also thought, how does it apply? And then I looked at what was the misconception. Okay, so as a result of this, these problems are really interesting. So if I get more number of problems from you guys, then definitely I'd be happy to solve such problems. Thank you, friends, for watching. And if you like this video, do share and subscribe to my channel for more updates. Thank you. This will really encourage me from doing more number of videos. Thank you.